Okay, so we will now construct the universal cover. So let yi be a sequence of covers of y. So where I is some set, which is in general uncountable. So let's look at all the yi's. So we take a fiber product of yi for I in this index set, and the fiber product y tilde with a base point. Okay. So we take a connected component of that. Then for any cover yi, there is a morphism because this yi is in the list, so you can see that will be in the list, so you can project to the cover. So universal cover is unique up to covering isomorphism because of the universality property, because it will have to appear in this list, so it will always there will always be a map from this y tilde to there. So then the uniqueness will follow from that. So the group of automorphisms of y tilde is called the fundamental group and is denoted by pi1 of y, and then so pi1 y acts transitively on y tilde on fibers. P tilde inverse x for each x in y. So to prove that, you need to choose one covering from class of base preserving isomorphism classes of coverings of y, and then you will have to do the fiber product with that, and then the universal cover with any base points will occur in the list, and hence map from y tilde to it will preserved in the base point. Okay. So that's how we'll prove this thing here. And then so because of this transitivity, you can see that the y tilde mod out by pi1 of y is actually y. Okay, so that's the idea here. So any covering of y or form y tilde gamma for a subgroup gamma is it will be some subgroup gamma of pi1 of y. Okay, so that's because if you so for the simply connected case, the universal cover will cover everything will be of this form. Okay, so that's because this group acts transitively, so any deck transformation group is any identification will be the deck transformation here. Again, that's very similar to the manifold case. So the isomorphism classes of coverings of Y is a set of conjugacy classes of the subgroups of pi1 of Y. Okay, so that's the same proof as in the ordinary manifold case. Okay. So the group of automorphisms of covering like this one is again similar is n gamma gamma. So n is the normalizer of gamma. So the covering is regular if and only if gamma is normal. So these are all same as in the ordinary covering space theory. And so good orbifold is a orbifold with the cover that is a manifold. So also another way is to say it's developable. And so that's it. The Happliger's terminology, and the good orbifold is Thurston's terminology. So a very sorry, this should be a very good orbifold is a orbifold with finite cover that is a manifold. Okay, so that's finite. So a good orbifold has a simply connected manifold as a universal cover. So any good orbifold with a cover that is manifold, so that's covered by some, again, by universal cover. Because it covers a manifold, then it means that it has to be a manifold. Okay, so because it only has a trivial mother, I mean mothers with trivial group. So that's anything covering it will have a trivial group, local group. So that should be a manifold. Okay, so we can also talk about induced homomorphisms of fundamental groups. So we'll only talk about the case when this is a orbifold diffeomorphism. Okay, but of course we can probably generalize it, but this is not so clear how to generalize this. So once you have orbifold diffeomorphism, then these will also go to orbifold diffeomorphism of the universal covers. And so once the lift value is determined at a point, then the lift is unique. Of course, you can always change this by the Dex transformation group here. And any homotopy of the orbifold maps will lead to homotopies of the universal covering map. So once you lift one of them, then the lift will be determined, just as in the covering space theory. So basically, we just consider the regular parts and the model neighborhoods where the lifts are clearly existent is unique. So the uniqueness can be proven this way, and the lift is also not that difficult to prove. So so we once we have an orbifold diffeomorphism, we have diffeomorphism of the universal cover. So therefore, we can obtain a map from the Dex transformation group to Dex transformation group. So that's a homomorphism. And if F and G are homotopic, then of course this map will be the same. Okay, the homomorphism will be the same. So that's some same proof. We can also do the path approach to the universal covering space. So we look at the G path. So we have some italic groupoid and the G path. So G is the arrows. Okay. So we'll have a G path is G0, C1, G1, CK. So over the some subdivision of interval AB. So CI are the continuous maps to this base space X0. And then the elements will be the ones with the starting point is CI plus 1 TI, and then the terminal point is CI TI for I1 to K. Okay, so it just goes from the one endpoint to the other. So CI is sort of a should give you connected path. So what these group arrows are doing, arrows are actually just the points, what how you identify these group points in X0. So this means that the CI plus 1 TI is the same as CI TI, okay, for every TI. So in the OE4 terminology. So arrows are the what gets identified. So initial point and so initial point is G0, and then the terminal point is GK. Okay, and then so um so that's what's called the path, and then the so there's also equivalence relation among these paths. So we can subdivide. So we can add a division point, and then you add in this identity trivial group identification arrow, and then you just replace CI with this, where these are restrictions. Okay, so there's a, and then we can also replace C with this different one. So for each I, we choose this continuous map of arrows. So we change the arrows in the continuous manner, and so that the so starting point of HTI is a CIT, and then the terminal point is CI prime T for each I, and so so what's happening is that you're changing yeah, so you're choosing different arrows actually, right? Uh, for these CIs. So CI is some points, but then you're using different. So by identifying with different arrows, there's lots of versions of CTI in the groupoid. So you just have to do a different choice of CI. So this is really not changing anything in the orbifold sense. They're the same points, but you representing in different X0. So this is a technical thing. But and so GI prime is going to be now the reversing I mean the identifying the endpoints. You just have to conjugate by these things. Okay, so that's all that it is. So it's really some sort of because x0 the same point can be represented in multiple different way in x0. So that's why you're doing this. And also you can compose two passes. So you have one pass and then another pass. And if the terminal point of this C equals the initial point, then you can do the composition of C prime C star. So to C double prime. So we let Ti double prime be the one divided by half, and then this Ci T to be Ci2T, and then Cit for bigger than T, I mean bigger than K, then you have to multiply by slow down by minus one half. So it's same as before. And these identifying arrows are the same for until K, and then after that you have to multiply by the GK, the first one GK, and then the rest is the same. Okay, so rest is the same. I mean, only up to you have to subtract by K, but you have to just shift. But only the first one you have to. So the end point here, the starting point and end point has to be the so the starting point of this G0 has to be the terminal point of this GK. So I mean GK. So you have to compose the arrow to get the right arrow to get the whole thing. Okay. So also the inverse is just you just reverse the T and then right. So this is for 0 to 1 only, right? And then you do the reverse of these each Ki. Okay, so that's just going in backward. Okay, so let's see. And then finally we can do the homotopy. So homotopies are just equivalences, and then the elementary homotopy is a family of G paths over the subdivision, so that this T, S, K, G, I, S, C, I depends continuously on S. So you just have to move these things continuously on S, the homotopy. But of course, they have to be passed, so they have to always match up. Okay, and then the homotopy class is denoted by C. And so this will generate an equivalence relation, and then the equivalence relation will be. Okay. Of course, that needs a proof, but the proof is very similar. So C star C prime is well defined in the homotopy classes C prime, and so we can define these. And of course, the associativity holds and up to homotopy, right? Not completely. And constant path like this is going to be the identity, play the role of identity, and the inverse will give you these, and so on. Okay, so I will not prove that all. So these are all very similar proof. So the fundamental group can be defined this way too. So you take any base point in x0 and 0, and then you look at all the group of loops based at x0. And the continuous function will of course give you so this is a deep homomorphism. Sorry, it is strange me. So if you have any orbifold map, this will induce a map like this. Okay. This is well defined up to conjugation, and so equivalence will give you an isomorphism. Okay, I mean equivalence of the orbifolds will give isomorphism. So we also the nice thing is that you can have a Seifert-Campan theorem. So Seifert-Campan theorem. So X be an orbifold, and these are union of two open sets, and then intersection is W. So assume that the groupoid restriction are always to U, V, W are connected. So this is some technical condition that that makes these so under the identification, these are all going to give you connected groupoid. Okay, so that's so you can restrict the groupoid to these open sets. That's fine. So to give you some sub-orbifold, sorry, there should be B here, but then of course this is a connected orbifold, so you take the pi1 of x0 is a quotient group of free product by the normal subgroup generated by this for gamma in here, and then the Ju is the induced homomorphism like this, and the Jb is the induced homomorphism. Okay. So those are all well defined things. Okay. So you can so the same idea works in this case. And finally, so if you have a group gamma acting on a connected manifold X0 properties continuously, and then gamma X0 has an orbifold structure. Okay, so this is the orbifold quotient we talked about from the manifold, right? So it will have fixed points, but it will still give you an orbifold structure. So any loop can be made into this path, one x c gamma, so that gamma x is c1 and c0 is x. So so there's the exact sequence going from pi1 of x0 to pi1 of gamma x0 to gamma to 1. Okay, so basic idea is that so these original loops will just still be loops, and then anything in gamma you can kind of make a group element here by this construction, but they are not well defined. Only they are defined only up to this, so that's why it gives you this exact sequence. Okay, so I haven't really proved that. So for example, if you have a two orbifold that is a disk with the arc silver, it has a fundamental group C2 because if you look at this is just the case when you have S2 with a reflection on gamma. So S2 has a trivial fundamental group, so this will be trivial and this is C2, so therefore this is C2. Okay, so that's the and the annulus with the one boundary component silver has a fundamental group isomorphic to G times C2. So that's because if you again look at this as so this is covered by the annulus with order 2 action. So we have order 2 action flipping the side, and this gives you G2 action. So this will be G2, and then original group is C. Okay, so it will be extension of G and Z2, but but this is actually trivial product. Okay, so of course we need to verify that, and so the basic idea here is that this is actually covered by some strip, infinite strip with the action by Z, which is continuous like this, and then the flipping by Z2, and then that will give you the orbifold quotient like this. Okay, so in that case, this will be trivial and this will be G times C2. So you can also verify that like this. And then the two-dimensional orbifold with cone points, which is boundaryless and then no silver points. So we can, so when there's no silver points, then the point is that you just have to remove the cone points, and then you can use a Van Kampen theorem to compute the fundamental group. So for example, teardrop with one cone point order n. So this is a union of it's a neighborhood of cone point with the disk. So disk has trivial fundamental group, and the cone point has a Gn as a fundamental group, but the point is again using the Van Kampen. So every element gets trivial, so everything gets trivial, and using the Van Kampen idea. Trivial. So for above 2, the fundamental group can be computed by using the removing the cone point and using the Van Kampen theorem. So if you have a two-dimensional orbifold and the boundary and silver points, so what you do is you can remove the neighborhood of the cone points and corner reflector points, and that will and then the fundamental group can be computed using Van Kampen theorem by taking open neighbors with silver boundary arcs, okay, and then the standard methods, and then you add up the Bohr neighborhoods, okay. So that's just using the simpler version of Van-Kempen theorem. So also fundamental group of three-dimensional orbifold can be obtained similarly. So here again, you just have to remove the highest codimensional singularity first, and then you go to the next dimensional ones, neighborhood of next dimensional ones, until once you can codimension zero neighborhoods, which are the silver points, and codimension one singularities, which are just mirrored points. There you can compute using the Van Kempen theorem because and then you can just keep adding the codimension one and neighborhood and then codimension zero neighborhood. So those way you can compute these. So for sidepod fibers three manifold example, so one can obtain a two manifold from a sidepod three manifold. So how do you do that? So we haven't really introduced sidepod three manifold, but it is ones which are circle filled with circles. So each neighborhood has is going to be fibered by circles, but you can glue the solid tape torus with some diffeomorphism of finite order. So how we can construct it is that the x0 will just be union of patches transversal to the fibers, and x1 will be the arrows obtained by the flows. So flows will give you the arrow. So flows will identify points. Okay. So orbifold will be two-dimensional with the cone points which are obtained as numerators of the fiber order. And fundamental group of X is a quotient of ordinary fundamental group of pi X by the central group generated by the genetic fiber. So I'm not really explaining that, but I'm just saying the result here. But basically idea is very similar to what I said, right? And so final topic is covering space and the fundamental group. So you can also be the theory of covering space using the fundamental group. So given a covering x prime to x, for any g path c in x, there's a lift of g path in x prime. So we can obtain, if you assign a initial point, then the lift is unique. So this is same as in the ordinary space. And then if x c prime is homotopic to c, then the lift of c prime is also homotopic to lift, as long as the initial points are the same. So we can prove that this fundamental group is injective. And the map from simply connected orbifold to orbifold lifts to any cover. So if the lift is unique, if the base point lift is not assigned, and so simply connected cover of orbifold covers any cover of the given orbifold. So from this, we can show that fiber product construction is simply connected and hence is a universal cover also. So using this theory, we can also get this theory. And so two simply connected coverings of orbifold are isomorphic. If the base points are given, then we can find the isomorphism resolving the base point. Okay, so those things all can be done, right? So simply connected covering of orbifold X is Galois covering with the Galois group isomorphic to this group. Okay, so Galois group just means maybe this just means orbifold covering. This orbifold group is this. So again, the proof is just that you look at the regular points and then you look at the inverse image and then you choose a base point from it and then so you can connect it with any path and then the path map to the fundamental group. So and the Galois group X transitivity on this pi 1 of X. So so you can then use this to identify the fundamental group with the Galois group. So so that's how you can prove this. So this is a Heppliger's approach to this here. And of course, you can also prove the existence of universal cover using the past approach. So so you just look at for orbifold, you look at all the set of homotopy classes of G paths in X. with some starting point x0, and then you define the topology of x hat by using open sets. That's set of paths ending at the simply connected open subset of U X with the homotopy class CD for D and U. So U here, maybe I shouldn't say simply connected. I mean the model model is simply connected, right? Um, and then you can define X hat to X by sending C to the endpoints, and then you also do the X hat times X1, which is the space of arrows for X. Then you can do these kind of G action on X hat. So this will make X hat into a bundle over X. And then you give a left action of pi 1 of X given by these formulas. And this will be transitive. So finally, we have to show that X hat is simply connected over. So that's how the Hapliga will approach this existence of the universal cover.